Good morning, everyone. I'm Jesse Sowell. I'm a member of the program committee, and I'm here to introduce the security track, which is going to be run by John Kristoff. I'm going to go ahead and turn it over to John so we can get started, and hope you enjoy it.
All right, very good. Thank you very much, Jesse, and the program committee for having us. Perhaps by show of hands, because I'm curious and interested, who amongst you has never been to a security track or what was a security buff before at NANOG by show of hands? Raise them nice and high. Now, those of you who have your hands up, look around who wasn't holding their hands up. One of the original ideas behind having the security, what was then the security buff, now the security track, is to help bring people in the security community together and build those contacts and networking. I think that's still one of the most important parts of this track. While we won't have a informal beer meet and greet in this room, anything that we can do to help get you connected into each other to network amongst yourselves, the better. If you don't have anyone else that you know to go to, you can always, you know me now, you can come up and ask me if you ever need help, like, I'm under DDoS, I needed to contact such and such. I may not be able to help you directly, but maybe I'm one hop away and I can point you in the right direction. So please take advantage of that. So we have three primary discussions today. And then if there's a little bit of time at the end, I'll mention something that I've been doing. This is this data plane thing. We have actually a pretty good diverse group of people. We have both physically and geographically and topic-wise. The first group of people are going to come up from Rackspace, who I don't think have been to NANOG before, but they're going to talk to you about some DNS exfiltration work that they've been doing. I think it's going to be some you're in for a real treat. I just met them this weekend. Probably most of us are meeting them for the first time. So let me introduce Corey and Nolan for Rackspace, and I'll just let you guys take it away.
Hi, I'm Nolan Berry from Rackspace. I'm a Linux systems engineer on the DNS engineering team in the NOC at Rackspace.
My name is Corey Schwartz. I also work at Rackspace. I've been there a few years. I work on storage operations engineering. So primarily, I'm not a DNS or networking guy. That's this guy's wheelhouse. But let you go.
All right, so we got an idea that we came up with kind of over lunch, just hanging out, about doing DNS-based data exfiltration, and we kind of just one-upped it and went from there. And we kept on adding features and functionality, and basically what we're going to be speaking on is it's not anything groundbreaking or anything new, but it's something that's almost always overlooked. And so, let's see here. Presentation up. One sec. Just waiting for our slide. So we are, going to be working, we're going to be giving our talk on DNS-based data exfiltration and botnet command and control structures. We're trying to get to the slides, yeah.
Are we able to switch to the laptop, the demo that they're doing?
Not the demo quite yet, but just the slides,
the
slide deck.
It's the DNS exfiltration.
If not, we can just... Oh, yeah. Oh, no worries. Yeah, we got that. All right. Wheel. So, well, I guess I'll just go over the basics of the concepts of what we do in our live demo. What we do is we basically take a concept where we abuse the authority section of DNS to route data out of secure environments where port 53 is allowed. And what we do is we take we took data, we chop up binary data, base64 encode it, and then use the local caches to route it to a malicious listening device that sews the packets back together, and then, well, base64 decodes it and then sews the packets back together. And then we took that a few steps further. We crafted false responses, and so there it looks like fake bidirectional traffic if you're looking at a TCP dump. We also created a malicious website in your browser if you visit it that will actually trick you into downloading a jar file that will then put you into a botnet that will then use MX record down channels to infiltrate data onto your network, and we can then swap out RSA, SSH keys, and root your box. And we're going to be doing a live demo of that ideally. But basically the reason this is an issue is most people don't watch port 53. Most people don't care about it. It's almost always open. And there's really no great preventative measure. You can detect it using big data analytics and pattern recognition. And to an extent, you can use RPZ. However, you can just get a malicious actor can just get a block list and get a new domain if they get added to it. So that's not exactly an effective method either. So with that, I guess we can just jump right into the live demo that Corey's going to be doing, and he'll do a live demo here of it.
All right, so great. This is the live demo portion. A lot of people have approached us and told us that we're crazy for trying to do a live demo on stage, but I think that this will work just fine. So what we're talking about when we're doing DNS data exfiltration, as my colleague Nolan said, what our strategy is to set up an evil DNS server and point the authority section for that. This is our strategy. We just went with the most simple, easiest to understand exfiltration strategy we could think of, which was, hey, let's just set up an authority for a domain that we own, allow the DNS existing infrastructure to route properly DNS traffic from clients to our evil DNS server. Our DNS server will make valid responses that appear like everything is operating normally, but we're going to be using subdomains as a channel for communication. And basically, we're going to use base64 as our encoding system, and we're gonna decide what type of traffic it is based on the record type. So A records, we're using that as the up channel. That is used in an A record that has a specially crafted MX or a specially crafted subdomain on the A record. That server will receive that, decode the base64, and stitch it back together. Similarly, MX records will be used for the down channel. So you send up, hey, what is this? What is the MX record for this domain? The server will take content, base64, encode it, and send it back to you. The subdomain of that being something that you want to send back down. So, for example, you can see on the slide there, hello world looks like that. It looks odd, right? You probably wouldn't expect someone to type that into a web browser. But how many of us actually see DNS queries like that all the time? Yeah, I see some hands. I work at Rackspace. We spin up cloud servers and cloud DNS instances. The DNS names of those automatically generated names looks pretty similar to that. You would look at that, it looks odd, but not really that odd.
Like a CDN or a cloud database or something like that. That's very common for
right.
FDN.
So if you're gonna approach a project like this, these are some things you have to think about. What does it actually look like to make a DNS query? These are straight out of RFC 1035. Basically, if all you're interested in is base64 encoding, you can basically ignore all the actual DNS protocol and just focus on the queue name, which, as I put here, is various size. The queue name format looks something like this. So you have like hello.something.nanog.con. The queue name will end up looking like this, where you'll have a number that represents the length of that record, followed by the record, a number that represents the length of the next record, followed by the next record. In binary, it looks like all that. So basically what we're doing in our exfiltration strategy is we're taking this first field and base64 decoding it. And if you think about what that actually looks like, it looks something like this. Oh, geez. Okay. So it looks something like this. If you're thinking about how all those bit manipulations look, it looks messy, right? If you're going to do something like this in Python, which is what we're doing, you do not have to do any of this stuff. All this like picking out fields out of the binary header, none of that is necessary. Python actually makes it very, very easy for you. That's this server 2. Python actually has a DNS library that will let you just manipulate A record types and MX record types directly. So this code is actually much more simple. I would recommend if anybody is interested in doing this, just do that. Don't try to do binary manipulation. Okay, so here in this demo, I've got a situation, or I've got a scenario set up here where I've got a local machine. This is just a client machine right here. Real DNS. This server is just running bind. It's a properly functioning bind installation where the domain nanog.con is configured for authority to point to fake DNS. So you can see bind is listening here. Well, I should have run that as root, but this is a properly running bind installation. So I'm just going to run TCP dump there so you can see DNS traffic traverse it. Okay. And this one is our evil DNS server. That's where I have my modified DNS server running. I'll start it right now. There we go. Okay, so let's see. We can see port 53 does not have bind listening, but it has this exfiltrate Python application running instead. So this is what that looks like. If I make any request to nanog.con, it will get sent to this properly functioning DNS server, and then will get forwarded on to this fake DNS server. You can see I've got some other DNS traffic going on, but okay. So how we use this? Simple dig. So this is what the word hello looks like in base 64. So in order to exfiltrate the word hello, you would just do this, dig a record type by default. So that dot file name, so I'll just call it like file1 dot nanog dot con. If I do that, you can see I got a properly formatted response back from the server, but on this server I have a file name called file1. The contents of it is the data that we exfiltrated. Of course, as I'm sure you all know, there are restrictions to what can be sent in an A record. There's restrictions to the length of each record. So if you want to send a larger file, you must first break it up into small segments. I have a Python program here that does exactly that. There we go. Let's say I want to send my password file. I'll give it, let's see, password. On the server side, I'll call it pwd. There we go. You can see what this program did is it broke it up into small chunks and it ended up sending these A record requests to the DNS system. Again, it looks odd. You wouldn't put that in a web browser. but you still might not notice it if you're the DNS infrastructure maintainer. And I can see there's a file here that has pwd on it. And there we go, pwd. Indeed, my password file was exfiltrated through the system. Okay, so that's all. That's a pretty good explanation of how it works, or at least the methodology. Of course, that's not really all that useful if you were going to try to use this in a hacking situation. If somebody's probably not going to run some strange like dig or ns lookup commands. You're probably not going to be able to convince many people to run weird scripts. So this is a more likely scenario. This is an end user doing what end users know best, which is looking at cat pics. So yeah, I'm a regular end user. I'm browsing my favorite website here. I actually have an account on this website. Don't laugh. I know I'm not the only one that has an account on a cat website. Okay, so I can log in. I've got, oh, it looks like I've got my member page. I can, all my favorite cats. Look at that. Oh, look at that. There's even an app now. I can click on that. There's even, I can get cats on my desktop. That is exactly what I want. Look at cats all day.
Move it to the bottom.
Oh. Let's see if this will ever. There we go. So here's my app. So I can look at cats. Oh, I opened it twice. Close that one. There we go. So let's do that. I'm just gonna keep that one open. I don't know. All right. So okay. So I've got this application that I run, and this is definitely something that I just want running all the time. What I want you to notice is that I can actually use this malicious application to do DNS exfiltration without the end user even knowing that it's being done. So here I am running this application. Let's say a hacker, someone who's got some malicious intent, goes in, they put in a command. Let's put this is a special feature of my evil DNS server. Anything that's in the command file gets sent down as the MX record. So I just put in, there we go. This is the contents of the MX record. So this application periodically checks for a new MX record in this style. Maybe I deleted it. There we go. So yeah, the client is basically doing an MX record request. If there is an MX record, if there's something in the command file, it will send the MX record response, which to this Java application is a command to send a file. So by putting .ssh id rsa, I've sent a command to this application to give me that file, and I can see now I have this application in here from the web app. And yes, that is a private SSH key. You would not expect Java application to in any way ever need to access that file, but yes, I can do that. I can ask for anything that I want, anything that the user who is running the application has access to. This application has access to.
We can infiltrate or exfiltrate. We could swap our key in for theirs. We could take theirs and use it. We could do whatever. Sure.
There's nothing that stops you from doing it the other way. Instead of giving it a command to upload a file, there's nothing that stops you from replacing the SSH key with your own. So yeah, this Java application has full access to everything that I have access to. one of the actually interesting things that I found out about Java security, oftentimes Java applications are not allowed to make outbound connections to domains that are not the origin domain. However, in some implementations of Java, specifically OpenJDK 7, I found that even though I can't establish an active connection to something outside of the domain I downloaded the website from, I can still send a command to do a DNS lookup. I think they assume that you're breaking the active connection, so no data can be transferred. But as we can see, that's not true at all. Okay, so this is sort of a hack the client sort of thing you can do. There's something else we looked at, and that was getting around firewalls. So for this example, we assume that there is a web server sitting in a demilitarized zone somewhere, and then there's a couple of database servers back here that are on a private network. So we assume that there's good tutelage in the firewall administration. Outbound connections are restricted from this private network. However, as it is often the case, there is a DNS server that you can still resolve names even though you've blocked TCP on the firewall. What that means is you can use this DNS server as a way to route traffic out, even to domains that you've explicitly blocked or you otherwise don't want connections to. So this is our strategy. We've found an existing exploit on a web server that allows us to send commands back to the database, and we want to tell the database to send us data that we probably shouldn't have access to. Let's take a look at what that looks like. So this is SQL1.sh. Okay. How many of you guys are familiar with curl? Curl, just want to make sure. Curl is a HTTP client. We're emulating being a web browser here. Actually, the page that I've hacked is this login page right here. So this page right here should be doing input validation, but it doesn't. So the username field allows you to pass additional parameters back to the database, and so I'm doing that with curl. Okay, so this line is a little hard to read, so I've got a description up here. This is the hello world of SQL injection. We're just passing the word hello. We're telling the database that we want the database to encode the data and then append the domain and do a host lookup. And you can see that all like in this complicated string right here. So if we run that, we can see I got a HTML page back. That looks pretty normal. And I've got this new file right here. The word hello, right? So the next example does a little bit more. This one, we're selecting a field that wouldn't normally show up. So we're selecting the password field. Again, this is a little bit hard to read, but we're doing select password from members, which that normally should not show up, right? I can actually I can pick any username, and it will tell me what the password is. So let's go ahead and run that. Okay, so if I check our evil DNS server, SQL2, that's the password field that was stored in the database. This next one is even a little bit more complicated. SQL3. This one, to be honest, like there would have to be some other things, some other bad practices put in place before this would work. But just for the sake of for the sake of demonstration. We're going to copy the postgres.conf file. We're going to use Postgres's built-in function read binary file. So similar to how we broke up the password file into 30-byte chunks and base64 encoded that, we're going to do a series of URL requests where we request 30 bytes starting at sequentially, like start with 30 bytes, give us 30, start with the next 30 bytes and give us 30, the next 30 bytes and give us 30. And we're going to run that. Let's do /SQL3. This one actually takes a little bit to run. You can see the DNS traffic really working hard. And you can see the SQL, that's the config file being copied from the database server. So using only HTTP requests and taking advantage of a SQL injection vulnerability, I'm able to convince the database to do things that it totally should not be doing. And what's worse is the security people thought that they were doing the right thing by blocking TCP. Of course, they should be sanitizing inputs too, but.
So I guess the next question that always comes up is, okay, so that's great and kind of scary, but how do we take care of it? What do we do? And that's where some of the problem comes into place. There's a lot you can do, but primarily it's you can do detection. Mitigation is pretty difficult. What we always recommend is a combination of big data analytics using Kibana, Elasticsearch, and PacketBeat, and you do frequency analysis of domains, but the problem with that is it's almost always after the fact, after the data has already been transmitted. You can use RPZ, you can use IP reputation, but that only works if you have a known, already listed bad actor. So there isn't a great, I mean, for high volume places, such as Rackspace, for example, where we have hundreds of thousands of DNS queries per second in our caches, 1,000 queries per second spike is not gonna really raise too many eyebrows. It's gonna kind of fly under the radar. And that's what makes this pretty, and you can also tweak it. You can make it even slower. You can add sleep timers to your for loop. You can make it go even slower. And it's a hard problem to really figure out because DNS was never really supposed to be the ultimate secure link in the chain. So that's one of the things that I think often people are like, okay, so you showed us this method. We all knew about it, but but what can we do to fix it? And I'm right there with everyone. I'm trying to figure it out. I just like highlighting the issue and bringing attention to it.
Yeah, one of the main things that we wanted to demonstrate here is just really that this is easy to do. These Python scripts that run the evil DNS server, they're short. They're not complex software projects that took like thousands of hours or anything.
We did them in an afternoon in a coffee shop for the most part.
Exactly. And this is something that you can do almost casually.
And state-sponsored actors have already been shown to be doing this exact behavior, and they have a lot more resources at their disposal.
Yeah, and even the detection is much harder to do than the actual act itself. We can do this in an afternoon and get a pretty decent evil DNS server running. How difficult is it to actually monitor DNS and do big data analytics? That's much more expensive. It's much more difficult to do, and most people don't do it. Large companies, we do data analytics, but as Nolan said, we might not notice some small potatoes like, oh, there was an additional 1,000 queries. No one would bat an eye at these even these unusual looking URLs. No one would investigate that.
Yeah.
If anyone has a quick question, maybe one or two questions, I don't want to trespass on the time of the others here, but if you have any questions for Nolan or Carrie, I think we'd be happy to entertain one. Just, I didn't mention this at the beginning, I should have, but it's better late than never. This session is being webcast and recorded.
Anton Capella, 5 Nines. Excellent work, guys. I do have a question though. How fast can you scale it? Like megabits, gigabits?
Yeah.
Where's it go? If you serialize it, obviously there's some round trips
So
wait for it, but
it's fairly slow. We transferred an ISO file from one data center to another, and it took like a couple days. But we've looked at a couple other methods like pulsing data, so we don't have to use subdomains. We looked into using multiple authoritative domains and spreading them across multiple receivers. Also adding hashes, so if we drop a UDP packet, it doesn't corrupt the whole file. We've looked into other issues, but
yeah, I didn't see any sequencing or scatter.
no, right now this is a
gather.
very quick and dirty thrown together in an afternoon proof of concept.
Could we just do torrents over it?
The reason,
Basically.
yeah, the reason why it's so slow and that no sequencing is necessary is that host by name, get host by name is a binding call in most languages. So you send a UDP traffic. Yes, it's UDP. It's not guaranteed to get there, but your application will block until it receives the answer. So that's the reason why no packet ordering or anything is necessary. If you wanted to make it faster to send more data without having to wait for a response, then you would probably have to implement something like that in there. But this was just, like I said, this is just the simplest, most straightforward way to do this, and the slowest, but still effective.
This is Stefan Lagerholm from Microsoft. Did you see this type of behavior in your environment, and that's what triggered you guys to do this research, or?
I had a friend who was called in to do incident response to a compromise for a company that had data stolen through subdomains, and we took that concept and just like tweaked it and made it like 10x more interesting. It was just straight credit cards were being sent out as subdomains. We took that and took it a few steps further.
But yes, this sort of thing happens in the wild all the time.
Yeah.
This is definitely not a one-time thing. There's even applications, much more complex applications built around doing this. If anybody's heard of like Iodine, for example, for DNS tunneling, there's ways to abuse the DNS system for its routing capabilities.
But our malware is 100% RFC compliance.
The next person I want to bring up is probably well known by many of you. Casey Claffey works for CADA. She had a colleague that just did a presentation an hour or two ago. She's going to talk about something we all probably have heard of before, but I think she has some interesting updates to talk to us about their spoofer project. So if we could have Casey's CADA spoofer project up on the deck, that'd be terrific. You don't need that. You'd like?
And this is
They need to bring up.
how many people have dealt with a DOS attack? Raise your hands. Okay, are the rest of you experiencing one right now and you don't know about it? Maybe. Okay. So I'm going to talk while the slides are coming up. I'm going to talk about some mitigation efforts my research group has worked on to deal with what I would argue is the biggest architectural vulnerability of the internet. And I should preface by saying mostly this is my work. Matthew Lucky, who's the first name on the slide, has been leading this project for a little over a year now. DHS funded it last year as part of their DDoS mitigation research and development program. So your tax dollars at work. And he's done an incredible job here. I just will give him kudos. And he would have come and give this talk himself, but he's in New Zealand. He has a faculty position in New Zealand, so he, for the sake of his kids, I'm giving this talk for him. But if you like it, it's his. Go send him mail and say it's great. So what's the problem we're trying to solve? So again, John said this is not a new problem. It's not a small problem. So Cloudflare reported in February a 400 gigabit DOS attack that was using spoofed packets. So spoofed packets are those that most of you probably know. You put a fake source address in the packet and you can send it out. And because the routers don't look at the source address in general to forward packets, you can then launch attacks with impunity. And indeed, it's also not a rare problem. So Cloudflare on the same blog entry back in February said that sometimes this is over 1,000 attacks a day using this spoofed spoofed sort of vector of attack. Just to drill down how these things normally go, often there's many other kinds of DOS attacks out there, but what Cloudflare was reporting on is what's called a volumetric reflection amplification attack. So you're an attacker, you put a fake source address, you send it to some server in the middle of the network, like a DNSSEC server or NTP, that will then respond to that packet with a bigger packet, maybe much bigger, maybe 10 or 100 times bigger. And then it goes back to the source address in the packet, which is the victim of the DOS attack. And thereby you can take a victim off the network or send so much traffic to them that they can't get any real traffic out. So volumetric reflection amplification attack, generally receivers have no way to know who sent the packet. Not a new problem. RFC 791 was written in 35 years ago, last month. So that RFC is now aged. It can run for president now. And RFC has been written 16 years ago was the first RFC, BCP 38. Which was talking about how to install filters to prevent these kinds of attacks. Basically, filter packets that leave your network to make sure that the source address is an address that you have, that is one of your networks or one of your customers' networks, and so it should be legitimately sending traffic out to the network. And then a few years later, because there was definitely some issues with how to do this with multi-home networks, it gets a little trickier. They published BCP 84, which is how to do this, what they call source address validation. Validate that the addresses are yours or under your auspices in 1984. So that's BCP 84. I will mention one thing about these RFCs, in particular BCP 84 talked about this notion of access control lists, which is, you guys are probably well familiar with them, but in this context, they were argued to be the best solution for doing this. If indeed your routing is not too dynamic and you don't have that many prefixes. So Matthew ran some numbers on route views and RIS data, so global BGP data over the last 14 years or so, more than that actually, 20 years. There was a time, indeed, when these RFCs came out, was a time when you could argue, and people did, that was a little bit tricky to do, the ACLs, because there was sufficient dynamics in the routing system, that is, ASs would announce different address space from month to month, that it would be tricky to keep the ACLs up to date. And of course, as you know, if you get one of those wrong, you might cut off a customer for the month and create all sorts of problems. What Matthew has found in the last 20 years is that this has changed. People are not changing their route announcements as often as they used to. In 2015, 5% of ASs in IPv4 changed their address space month to month. It's even smaller in v6. So this is one thing I think to take into consideration when we're thinking about how we want to deal with this issue in the large in terms of industry norms. And just drilling down even further on this point, if he just looks at August data of this year, almost 90% of stub AS networks could do this kind of ACL with 4 prefixes. And indeed, 4 years ago, they would have had the same ACL. It just half of them would have had the same ACL. It doesn't change that often. So again, sort of time to revisit maybe how we think about doing default approaches to these problems. Now, the problem is, even with all of that, there's still a massive incentive problem here. There's no incentive for an ISP to do this because it helps who? It helps everybody else on the network. It doesn't help that ISP. In fact, again, you do one thing wrong, you make a typo, you possibly cut your customer off. So there's counter incentives to doing this on some networks. Nonetheless, what we do see so far is that most networks do this filtering. In fact, most US broadband residential networks are doing this. No? Okay, so I have some arguments come up to the mic at the end. There's some issues with business networks. Again, enterprise networks or multi-homing may be going on. The defaults may be different, so we can talk about that at the end. But certainly this kind of filtering gives an operator the moral high ground to go pressure other people in the ecosystem to do this filtering also. We saw something similar to this in the 90s with the route aggregation list that Tony, as I remember, would post to the NANOG list about if you could be doing more route aggregation, it would be better for the global routing table, sort of environmentally sound, by using transparency, by publishing the networks that were not doing it. And more concretely today, we do see evidence that insurance companies who are trying to provide cyber insurance will take into account security hygiene practices. So we can imagine this being used as one such practice. The problem is, and of course ISOC has launched this collective action group, the routing manifesto, to try to get people committing to doing these kinds of, achieving these kind of norms. The problem is there's no public data that lets a network show that they themselves have deployed this kind of filtering. Or see if other networks have, like people they might want to peer with. Like it's not a field in peering DB yet, although it could be. There are 2 projects. One of them started by Jared, who's in the audience, that do allow detection of which networks have not deployed filtering, but it sort of relies on buggy open resolvers, DNS resolvers, and you can't sort of go test a specific network. He's at the mercy of whatever data he collects on the open DNS resolvers. And then there's the MIT project, which is 20-year-old, maybe 15-year-old project by now. It started by a graduate student at MIT, Rob Beverly, which aggregated statistics of these some spoofing tests from within networks. So you would download a piece of code, run the spoof test to his MIT server. He was a graduate student at the time. You had to manually run the test, and he didn't do any public reporting. That was a long time ago. So that's basically the system that we are building upon, Rob's system, and he's a collaborator on the project and giving us lots of feedback. Okay, so what's the basic architecture of the system? Unlike many other types of measurements on the internet, where like you can measure DNSSEC compliance by sending a packet from anywhere on the network to that server to see if it does DNSSEC, you cannot do that with spoofing. You really have to get behind the network if you want to test a specific network and try to send a spoof packet. So that's what we do. We have a client that sends these spoof packets, same as the old MIT architecture. We send them to our own vantage points, these few packets. We then analyze which packets got through and which packets didn't, and in some cases where along the path it might have been filtered. We do a computation, we provide public reporting, we let you have access to your own data. Now we let you have access to anonymized forms of everybody else's data. We test routed and private addresses. We test v4 and v6. We do something called trace filter I mentioned before. It's essentially trace route with spoofed packets to try to gauge exactly where in the network the filtering is or is not happening. And then we also test IP addresses outside the prefix that is the original prefix inside the network. So maybe the /24 can be spoofed, but the /25 can't be spoofed. 23 can't be spoofed. So we try to, and I'll show you some examples, test how many addresses in the same network prefix can be spoofed. New features of the system, and if you're bored by this talk already, you can save time and just go download this yourself at spoofer.cata.org. That's really my goal for the talk, right, is to get 1,000 people to download it. Hopefully not a DOS attack on my web server, but let's think of it as performance testing my web server. The new features of this system is, by default, we share the results. So this has been a big debate in the community about whether this is a good thing to be transparent about, because after all, it's a list of networks that allow spoofing. And indeed, for 10 years or so, the default was not to share. And we've had lots of discussions with operators, and it's one of the things I'm happy to take feedback on here about whether it's time now, we're again 35 years after the RFC is published, this problem is still not fixed and it's still a major vector of attack. We're going to try the whole transparency approach. So we're sharing anonymized results by default. You can opt out if you don't want them shared, if you just want to test it on your own first to get it fixed. But by the default is it shares. And by default also, unless you opt out, we share unanonymized results, so exact IP addresses where spoofing is allowed, with remediation authorities like certs. So we've had certs for certain countries come and say, I want all the tests for country X, and yes, we can make that available with raw IPs. Also, enabling us to increase exponentially the number of tests we get is that once you install this on your laptop, please do, it runs in the background. Every time it sees a new network, it'll test the network. And that's really enabled us to get a lot more tests than old versions of this. Test once per week, because things might change. Network upgrade, maybe you forget to install the filters. And we have a graphical interface so that you can browse the results of your test or schedule future tests. And then finally, we have a reporting engine which publicly shows the outcomes of those tests that are shareable, which allows users to select by country, by AS, by your customer's AS. All of that's at this URL. If you just go to spoofer.cata.org and click on recent tests, you can look at that right now. I'm not going to do a live demo, but hopefully you guys will during this talk. So some people are twitchy about the word spoofing and say, well, if you're doing any spoofing at all, it's an issue. We've really thought about this hard. Again, it comes down to cost benefit and are you going to try to clean this up or not? Maybe this won't work and we'll have to try something else. But I really think any solution, if you're going to stick with IP as an architecture, is going to have to have to include measurement of whether spoofing is allowed on a network. So as mitigating factors, we send these packets very slowly. We're not sending a stream of packets. There's no way this can look like a scan, right? We send a couple of packets, one routed, private, a few more than one, but and we send v4 and v6. We send it only to machines that we control. So there are measurement infrastructure servers. We do see operators using it for remediation. I'll show you an example of it. But mostly, I don't see another approach to this problem. Okay, here's the user interface. Maybe some of you have seen it by now if you've installed this in the last 10 minutes. It's not Angry Birds. Sorry, we're not. We haven't gamified this yet, but it lets you see the results of your tests. It lets you schedule future tests. We have signed installers for Mac OS, Windows, Linux. Source code's available. GPL, license, C++. Here's a time series of tests that we've run. Actually, this is all over the last 10 years. So this includes before when Rob was running his stuff from MIT, and then some downtime when we realized we really need to put some real funding behind this. Rob did all this work with no dedicated funding. There's good stories about that I can tell you offline. But since we released this new client in May, where the red arrow is, we've seen a lot of new tests run. And we have not done any real big announcement of this. Matthew gave a talk on NZNOG last month, and so this is the first talk to operators. So hopefully we're going to see a jump this week too. You can go look at that time series online yourself if you click on stats on the website and see what impact you've had. Okay, reporting engine. Low-level details here. You can go click on recent tests. This is what you see. Actually, this isn't quite what you see because I've typed in USA. I want to just see all the tests from the United States. The most recent N tests from the United States. And then there's a link at the bottom to go to previous tests before that. So you see timestamp client IP. You see IPv4 and IPv6 being tested. Do I have a laser thing? Yes, I do. So if you V4 and V6 anonymized, you see whether the packets were blocked. All right, so I'll just go forward. You see, okay, so the red is received, the packets were received, and then the V4 adjacency is within which size of prefix could you still do spoofing. And then the full report on the right is you click there and you get a full report, including a very nice topology graph of exactly where the filtering, we observe the filtering to be happen. Anonymization is 2/24 for V4, 32 at the moment for V6. We're probably going to go up to /40 unless anybody tells me that's a terrible idea for some reason for V6. And just to preempt the concern that, well, if I'm behind a NAT, this isn't really going to give useful information. It gives incredibly useful information behind a NAT. NATs do all sorts of different funky things, as you know. Some block traffic, some rewrite the packet source address and send it on if it's spoofed. So go figure. And then some just pass it on directly. Some networks will filter for V4 and not V6. I'm sure that's not a big surprise in this room, but we see it. So. And lastly, what can you do to help? Yes, please install the client. That's really the main reason we're here today. Well, I want to get feedback from you on not just the client and using it, but other issues surrounding spoofing. I'll get to that. It's particularly important, not even just for operators, but people who travel a lot and go to a lot of edge networks, because, right, we're trying to test the edge mostly. So this is a great opportunity. Any room full of 500 laptops is like Mecca. And again, NATs are still useful, so don't worry about if you're usually behind a NAT, are you going to get useful results? Yes. So we do see Matthew at the moment is staying up late and sending the results of some of these tests to the technical contact for the network. That doesn't scale, obviously, so we're going to automate that. But at the moment, he's doing this by hand. And we do see that people are using this to remediate their own network, so that's pretty awesome. It turns out to be tricky. You don't always know if the filter you've put in place is doing the right thing, so we're happy to see it being used in that way. Now, obviously, one of the other typical objections to this type of work, this crowdsourcing of measurements, is the sample bias. So you have to download the code, and the people sort of maybe you get a not representative sample of people that are downloading it. So tell your families. Tell your families to download it too. So we're trying to look at other sources of data. I'm going to talk about two different types of data. If you have enough traceroute data, and CADA happens to have many, many millions of traceroutes, you can use it to see a specific type of lack of filtering, which Jared actually gave us this idea. You can infer that customer provider links to stub ASs are not filtering. And let me show you an example. The stub AS here is on the bottom. If you see a traceroute go from provider 1 to the stub AS to provider 2, you know that the stub AS is not filtering and provider 2 is not filtering. Now, we can have a long debate, and it's kind of been had on the NANOG list about which of those networks should be doing that filtering. I don't need to have that debate now. That's an interesting thing to talk about. Maybe the panel wants to talk about it, but in any event, we can tell with some traceroute data that when it's not happening for a certain subsample, not that big of a sample, but it's another view into the macroscopic issue here. And Matthew just submitted a PAM paper, a fantastic paper on this topic if you want the gory details. And here's an example of traceroute output where the customer provider link is not doing the filtering, and you could even generate a sort of automatic ingress ACL for that network if you wanted to go a step further, and that's what we're hoping for year 2, 3, that we automate some of the remediation possibilities here. Again, the goal over is to develop a topological method to infer lack of ingress filtering so that we can take advantage of many archives of traceroute data that are out there. I probably should have had this slide earlier. So in terms of like whose duty is it really to do this? I think that, we see providers trying to clean up other issues now. You'll have an IoT talk tomorrow, I think, that might talk about what is the provider's responsibility or not to clean up devices in the home that are launching these attacks. Same goes for networks that are behind a provider. I think that these issues will come up, so maybe it's not totally clean to just say, well, that always the edge network should be doing the filtering and never the ISP of the edge network. I'll talk about that also in a second. But to just repeat that maybe one thing we can consider, regardless of whose problem you think it is to do this, whose responsibility, that it's probably time to reconsider the defaults. Like both the defense and the offense parameters in this space have changed dramatically in the last 15 years, right? Lots more attacks, lots more opportunities, and a change in the stability of the system. So maybe it's retimed, if not unicast RPF being a default, maybe at least these static ACLs will be a default. And again, we're going to try to make it easier for ISPs to do that. So where to? We really want the network to have the data to have operational impact and improve the hygiene of networks out there. So you can help today, right now, if you haven't already. Please go download the tool. Tell us if you have any issues running it, installing it. And of course, I'm interested in what issues you encounter when you do try to deploy filtering. We've been answering some questions along the way from smaller ISPs who just don't have the expertise. And we're happy to try to do that or point people at other people that have more expertise than we. So if you'd like to be a volunteer in that space, let us know. And we're also working on a per provider view. So you could type in your AS number and we could tell you not only your AS spoof test, but any customers that are in your customer cone as we infer it from BGP, which might help you if you're interested. We're also trying to make it faster. The probing itself is not super fast right now because we're not trying to be super fast, but we're working on that. And then the second source of data that I'm interested, if anybody here is willing to play, is we can actually look at this through IXP traffic data. If we have sanitized ISP traffic data, so we just need the MAC address and the source IP, and we know enough about the IXP, so the members that are at the IXP, we can infer their customer cones, and then also figure out, at least estimate, this isn't foolproof, but we could give a hint, that, well, that traffic shouldn't be going through that interface on that IXP switch because it's not in the source address isn't in their customer cone. And we could help, either IXPs help their members get cleaned up, and IXPs could use this as some kind of competitive advantage that they're offering this service, or we could help the networks directly. So please let us know if you or you know some friends at IXPs that are willing to either run our tool that we have to do this sort of thing that Matthew's still working on, or send us sanitized data that we could run it ourselves. So that's it for me. I'd like to, again, mention it's DHS funded right now. DHS is also funding NIST to do some performance assessments of how routers handle this kind of demand. I know that's an issue for some providers. There's a sense of you either forward or you check filter. So there is work going on in that space. There's a URL if you're interested. Any questions, send to spoofer info. And there is a donate button. I forget who asked. Matt asked earlier about donating to the Periscope project. Yes, the university takes donations. In fact, we take them and they're no overhead, which is remarkable for a university. So click on the link, donate link at the top right corner of the CADA website if you're interested in donating to this or any other project. You can specify what project you want to fund. I think that's all I've got. Questions? Yes, thank you.
Etika Ko, Farside Security. I would encourage everybody in the room to take a look at this tool. For 15 years, there's always been that, yeah, we have a lot of spoof traffic DDoS. No, we don't. Yeah, we do. No, we don't. And there really hasn't been really good measurement. So while this work was started at the MIT Spoofer project like 15 years ago, right, there was a significant uptake a couple of years ago where CADA got the grant because there was an understanding that a lot of spoof traffic is still happening. And we're not doing our job to help that. Either ingress filtering by ISPs, right, which is the BCP 38, or egress, which for those of you that are from enterprise networks, I would hope that you would start doing. So downloading this tool will at least give you the ability to see whether or not spoofability is possible from your networks. So thank you, Casey, for the talk.
Hi, Rob Hagens from Zayo. Thanks for the work. It's definitely interesting. We have a lot of customers who have a NID at the end of our circuit.
What's that?
Just a network interface device.
Okay.
it can be used as a test point. It can be used for various things. It would be interesting to think about having that do the spoofing analysis occasionally
Yep.
to then give us as an ISP information about where our filters are incorrect.
Yep. Yes, we've talked about, and in fact, you can see the tasks that we planned for this project. It's up on the website too. And one of them we're still thinking about trying to do is how to get this inside OpenWRT platform so it runs in home CPE devices. Yes, and obvious, not the only measurement we could conceive of putting in there that would be useful for users and operators. Yes.
Hi, Aaron Hughes, 6 Connect. 2 points. One, I think it might be useful to reach out to RIPE to see if they can add this to the Atlas project and get it on all these probes, and you'll get a lot of data.
Yeah, that's happened. And maybe if somebody from RIPE is here, they can talk about it. But essentially, it's not RIPE is not comfortable with that for policy reasons.
Okay.
So out of our hands.
And the second is, it might be useful. I'm not sure if the DHS funds allowed for it, but useful to write some toolkits to help people deploy filters, because still there are a lot of network operators that are not comfortable with IRRDs and PGPQ3 and catting to RANC-W and validating things are being written correctly for prefix updates that are automated.
Yes.
And there's so few tools out there available that I think the level of comfort for a lot of operators in just that scripting is low, and that's the real unfortunate problem. If this were easier for operators to just download a package, install, and point at their routers and push out for customers and edges, I think there'd be a lot more uptake on implementation.
Yep, great comment. We're trying to go in that direction with the sort of automated generation of ACLs for networks where we think we can do that with some level of confidence. There's obviously some concern about our confidence in whether they're going to work, but yeah, we want to go in that direction. It would be great to talk to operators who might want to help us on the other side with some specific use cases that might be generalizable.
Over here.
Sorry.
Hey.
Hey.
How are you? Tony Tauber, Comcast. Great work. I'm a big fan. And I noticed on the website also there's Ubuntu packages.
I didn't. Yes.
Source code. So I don't know. People have VMs in various and sundry hosted places. Might be interesting to see what's
Yep.
going on in those, since obviously they have much bandwidth that DDoSers can make use of.
That's a great suggestion. I'm going to put that on the slides. Thank you, Tony. Yes.
Hey, Kaveh Ranjwal, RIPE NCC. Just to answer to Aaron's comment, yes, for policy reasons, we don't allow spoofing from the probes, RIPE Atlas probes, but actually I know that our engineers are talking to add this data to RIPE stats, so you can actually query when you're looking for a resource, you can then see in that network is spoofing happening.
Oh, that's cool.
That's what we're doing, that kind of integration.
That's cool. Thank you. Great. All right. Well, I'm around the rest of the day. I'm not here tomorrow, but if you have any other questions or suggestions, please come find me. Thank you.
Thank you again, Casey. We're probably not going to have time for me to talk about this last item, so if you want to know anything about it, there's not a whole lot to say, but the page that's just not there yet. So I'd like to bring up our last main contributor, or set of contributors here, from 360 CN. I'm not going to try to pronounce at least one of the gentlemen's full names. I'll let them do that because I'll butcher it and embarrass myself. They're going to talk about some DDoS work that they're doing that I think you'll find quite interesting.
Hello, everyone. Let's talk, yes. So today we are going to talk about our free DDoS monitoring project. And first, about 360. Probably not many folks have heard about 360, but actually we are the biggest security company in China. We have huge amount of users. And about us, I run the network security research lab at 360. And recently we have released quite a few free tools for the security community to use. I'm gonna go over a few here. First one is of passive DNS. So for security engineer, probably PDNS is not something really new. Just now, these two Rackspace gentlemen talks about DNS infiltration attack. Actually, PDNS can be a very good tool to study that kind of behavior. And our PDNS is the only public known DNS, passive DNS system in China, which covers about 10% of all Chinese DNS traffic. So for security researchers, this system is free to sign up. You can go take a look. That's the first one. Then there's our scan mount. We all know internet web scan happening all the time. In the past, I couldn't find a very good site which tracks all the scan activities, and I can look up the data from all the angles. So if you're like me, you're gonna like this system because we log all the scan activities and you can study the data from all the angles. It's worth taking a look. Then the open data. We also have quite some free database available for you to download. For example, EK, we have more than 20 DGA families, and also Mirai scanner. This is the new botnet, DDoS botnet. Yesterday, we just released a free list for you to download, which covers more than 500 million infected IoT devices. And now it's the DDoS mount. That's the system we're going to talk about here. Motivation, why we need DDoS mount. We all know DDoS is one of the biggest security threats these days on the internet. But I personally feel like we really lack the needed visibility here. Originally, I wrote most of the time only the victims and the providers know what happened. And then I cross it off. As in reality, we all know there are lots of times even the victims and ISPs, they don't exactly know what has happened. So we built this system because we already have this system in place. We figured why not just give free access to the community. The system sees average more than 20,000 attacks every day. I think that puts us on top of the spot. Probably is one of the biggest platform on the internet, I guess. And we are highly confident if you see a fairly big attack, the system will see it, and you can also look it up. Here's the news. Everybody knows about this, I guess. Corruption Security was attacked mid-September. I think everybody knows about this. But again, that's just news. There's no fact. There's no data. Where's the data? Show me the data. And here we go. Like I mentioned, first from the scan mount. This diagram shows the last 90 days of port 2323 scan activities. You noticed since around September 6th, there's an uptick for port 2323 scan activities, both from the total counts, unique scanners, unique/net blocks, unique AS. So we see the scan going up. Then on our HoneyNet, you will notice the last line, probably the font a little bit small, but you will see the last line. Apparently, this Mirai is trying to use username admin, password 12346 to infect more devices. And then, what we see from our DDoS mount, this is a public available website. You can go there and just take a look. You can enter any IP or domains to look up if there's any DDoS incident going on with that IP or DNS name within the last 30 days. Let's see, if you entered corruptionsecurity.com, and you get this, something like this. The first part, see, there's the UDP amplification attack that happened on 14th this month. And then the next one is the DNS flood. Again, this month on the 12th. And then the next one, a little bit interesting. That's a DNS random subdomain attack. The system shows the first 30 subdomains here. You can take a look. It's pretty interesting. Then the last one is TCP SAM flood attack. And if this page is for user who is just a visitor. You don't need to sign up. So you can just go there and look it up. But if you do have an account, you get this more detailed breakdown for the attack. You will see the time frame, the traffic, the source and destination port heat map, the top source and top destination IP, and top source and top destination ports, packet size distribution, protocol distribution, TCP flags distribution, and top attackers. Actually, we have even more interesting things. We also have a botnet command tracking system. This is our secret sauce. Basically, we tap into the command and controller of the DDoS botnet, and we pull the data. We pull the attack instruction in real time. And just yesterday, we successfully tapped into the Mirai DDoS botnet, and we started to pull the attack. And also, like I mentioned, on this link, there's the Mirai botnet IP you can download for free, which covers more than 500 million of infected IoT devices. With that, I'm going to give the mic to my coworker, Keqiang. He's going to go over the details about the DDoS mount.
Hello, my name is Keqiang. I am one of the core developer of DDoS mount system. And I will mainly introduce how does DDoS mount work from a technical perspective. In short, DDoS mount mainly based on three major components. Firstly, the real-time net flow traffic, which focus on layer 3 DDoS attacks detecting. Secondly, real-time DNS traffic, which contribute in three major aspects. And we also run a real-time DDoS botnet command tracking system. First, we talk about the real-time net flow traffic. This small system collects huge volume net flow from various networks. Multiple internet service provider, which has cooperative relations with us, export net flow traffic to us from large network backbone routers, and some of the users of DDoS mount system contribute net flow records to us. And currently, we handle more than 30 billion net flow records every day, and all the data is processed in their real time. In our approach, net flow-based attack detection mainly include two steps. The first important step is the spike detecting. When an anomaly spike event be captured against any IP, then the program will jump to characteristics recognition, and the program will analyze the raw net flow records to detect attack vectors. Due to different DDoS attacks, attack vectors usually present certain characteristics on net flow traffic. Okay, I will give an example on how we do it. On September 14, we saw an attack against Bank of America, and this is commonly the Bank of America traffic look like this, and this is the traffic figure during attack happen. We can see an obvious spike from the net flow traffic. And when the spike event be captured, then the characteristics recognition program will start work. And to analyze the raw net flow records, let's take a look at the raw net flow records of the Bank of America. And from the source address column, we can see most of the traffic is come from the UDP port 123, 190, and 19, and here you will know this attack is typically UDP reflection attacks. The raw data is slides, but not everybody can read the raw data. And this is how our system show the data. And from the figure, you can see the top 5 source port by based on statistic the raw net flow records of Bank of America. And from the red table, we can see most of the packets from suspicious source port, such as the number 1 is UDP port 53, which is generally be used to launch the DNS reflection DDoS. The number 2 is UDP port 190 is generally means SSDP based DDoS, and the UDP port 123 is NTP based DDoS. UDP 19 is charging based DDoS. And these 4 UDP protocols are the most popular be used to launch the UDP reflection attacks due to the amplification features. And from the characteristics of source port, we know that this attack is mixed traffic. Let's let us take a look at the protocol and the packet size. It's mostly UDP traffic, which is not normal for web traffic, and the packet size are mostly 1500 bytes, which is like reaching the MTU threshold, which is not normal. And from this, this example illustrates 2 steps on how did a small system detect DDoS based on net flow traffic. And next, I will introduce the second important data set is real-time DNS traffic. We process 240 billion DNS requests every day, and which covers about 10% DNS traffic in China. And Yimin also has already introduced, we also run a passive DNS platform. But in our approach, why we need DNS traffic in a DDoS monitoring system? What can we get from DNS traffic? Well, real-time DNS traffic mainly contributes in 3 aspects. Firstly, the ability to monitor domain instead of just IP. This is easy to understand. The net flow are just IP dimension data, and combine the DNS traffic, we have the ability to monitor domain objects. And furthermore, the DNS traffic can improve the accuracy of the detecting against DNS reflection attacks and the random subdomain attacks. For the DNS reflection attacks, let's again use the Bank of America as the example. We have detected DNS reflection attack vectors from the net flow record net flow records, and combine the DNS traffic. We can describe the entire attack procedures. And basically, the attacker used the BOL address as query source to ask lots of open DNS resolvers for domain CPSC.gov, and then the DNS response from the open resolvers flood BOL address. And here, the key point is the abused domain CPSC.gov which is captured from the real-time DNS traffic. Now, why is CPSC.gov? Let's take a look at the D command, and you can run this command D CPSC.gov ending plus TCP, and you will get the DNS. You will find the DNS response. This DNS response package is pretty large, and the reason why we have a so large response is because the domain CPS.gov has DNSSEC enabled, so a small request can generate big response, and that's why the attacker loves this domain. What else? The left figure lists the top abused domain, and the number 1 is CPSC.gov, nearly 60%, and the number 2 is divcon.gov, and then is doc.gov, AIDS.gov. And here is pretty interesting. The .gov seems is quite popular here. And on the right side is a live feed from our system, and it shows some ongoing DNS reflection attacks. And this type of attack seems is popularly stands. And for example, we detected more than 72,000 DNS reflection attacks in just 7 days. Let's take a look at another type of attack, DNS random subdomain attack. We know when DNS request asks for some long unknown domain, and there will be no local cache, and all this query will reach the authoritative server of the domain, and in this attack, the attack target will be is the DNS authoritative server. I will use the attack against target xinyu3egg.com as an example to introduce the DNS random subdomain attacks. On October 9, we detected xinyu3egg.com, which is an illegal gambling website, was attacked, and at this time, our system captured more than 14,000 random subdomains we used to launch the attack. And from the figure, we can see a lot of the all of this random subdomain probably will reach the authoritative server of xinyu3egg.com eventually, and the authoritative server of the xinyu.com will be knocked down finally. The DNS random subdomain attack is not so popular as the UDP reflection and SYN flood, but in our system, we detected more than 3,000 random subdomains in a week, and this is still a big number. Okay, the last component is the DDoS botnet component tracking system. We have run a live DDoS botnet C2 tracking system for a long time, and we have detected nearly 190 C2 servers, and we logged nearly 600 million DDoS related attack instructions. Nearly 40 common DDoS families are being tracked, such as the ELK node, as known as beer gas, the XOR.DDoS, the Miss Black, and so on. We still use an example to introduce the DDoS botnet tracking system. On September 23, we detected Microsoft was SYN flood, and at this attack we detected 18 related C2 servers, and our system logged multiple C2 attack instructions. The table listed a little part of the attack instructions. And next, here we are looking at one specific attack instructions. The C2 family is LDS, which many used run on Linux machine, and most commonly be used to launch the SYN flood and UDP flood. And here we have the C2 server, C2 pod, and the real-time instruction. So basically, the C2 server is asking the boss to launch the SYN flood target Microsoft on HTTP port. Okay. Briefly recap, how does DDoS mode detect DDoS? Basically, we combine that real-time net flow traffic, real-time DNS traffic, and DDoS botnet tracking system together. Now, welcome use the DDoS mode system. The DDoS mode, the usage is pretty easy. Just applying a free account and create monitoring object. You are interested in the objects could be IP, net blocks, FDN, or DNS zones. Then the system will take care of the rest automatically. And if an attack happens, you can receive the email notification, and you can view the report and get insights about the attack. Contribute more net flow data. It means more coverage, so the contributed net flow will always be welcome, and the submit DDoS related malware samples is very helpful for our DDoS botnet tracking system. Okay, that's all. Thanks.
Quick question, Matt Petak from Yahoo. If you've got commands being logged, 600 million commands on DDoS command and control nodes, that means you've got an eye into attacks basically at the point they're being launched. Do you do any kind of proactive notification of targets that are, hey, guess what? There's a DDoS attack that's being launched against you. Here's the nature of the DDoS. Many times the victim of a DDoS spends precious time trying to characterize the nature of the DDoS attack. Is it volumetric? Is it SYN floods? What kind of attack is it? If you've got the commands that are being executed at your fingertips, it really would be helpful to be able to provide that to the victim to say, I already know what kind of attack it is. Here's the commands that were being executed against you. This is the traffic you need to filter out. I think that would be a great offering if you could make that available.
Actually, we already have that in place. The only thing you need is just apply a count, and you get that report.
Awesome.
Yeah.
Thank you.
All right, Rebecca Kao, Farside Security. So I've seen Yiming now in 3 different continents in the last, 6 weeks. And I am super happy that he's evangelizing this work. I mean, some people might be skeptical because of, some other issues. I love his work. He's a great contributor to all the operational security areas. And it's taken many years, right, to develop this. This isn't something that he did in a coffee shop, right? I mean, sorry for Rackspace, but, but it is, I mean, it's excellent and, it's free. Utilize it, see how effective it can be in your environments, because we have to get better at mitigating all the crap that's out there. Thank you.
Thank you.
I'll just make some closing remarks. Thank you very much, gentlemen, and to all the panelists, Casey and Nolan and Corey.